What is up, amigos? Today we're talking about how to calculate the Reynolds number, and this may seem like a fairly obvious thing, especially if you've seen this video which we've done on the Reynolds number and what it is and its limitations. In this video, I hope you'll find that it's not exactly as straightforward as what you might expect. So we know that the Reynolds number is very important for determining things like whether something is going to be laminar, turbulent, whether something will propagate more downstream or not from that video that we have done a while ago. But we know that Reynolds number equals the density times the free stream velocity times the characteristic length divided by the dynamic viscosity or the kinematic viscosity if you then factor out the density there. So this seems fairly obvious. I mean, we know what the density of air is, like it's in the system. We know what the free stream velocity is, that's also in the system. We know what the dynamic viscosity or the kinematic viscosity is, that's also part of the system. But this value here is the troublesome one. So what is it? Well, let me give an example to show you how it can change and what we would pick based on what we want to find. So let's say we have the free stream flow coming in here and we have an airfoil. So a fairly simple shape here. And let's say, and then we have the leading edge here, trailing edge here, and let's say we have a vortex generator at one point. So we know that the chord here is 1 meter. We know that the span is, let's say, 2 meters, and we can say the thickness, whatever, we know what the thickness is based on the profile. And now for the vortex generator, we know the length, let's say it's 0.1 meters, the width of it is 0.2 meters, and let's say the height is 0.1 meters. And let's say the free stream velocity is 1 meter per second. So, and the density, let's say, is 1.2 kilograms per meter cubed, which it may not be, usually it won't be, but let's just assume that for now. For this purpose, it doesn't make much of a difference. And the dynamic viscosity is 1.7 by 10 to the negative 5 Pascal seconds. So knowing all this information, we should be able to calculate the Reynolds number. But which value do we take for the length? This is where we have to understand what we want to find and what the flow will be doing. So remember, we have a vortex generator here and we have the airfoil. So let's say I were to want to find out how an airfoil performs with a vortex generator, just a vortex generator, not a specific vortex generator, just a vortex generator. Well, that indicates to me that the type of vortex generator is not exactly that important. What's more important is the airfoil itself, because I'm interested in the airfoil and just with a generic vortex generator. In that case, I would be more interested in knowing what the airfoil does. What's more, I know that the airfoil will affect the flow and determine whether the flow will be largely laminar or turbulent. Of course, the vortex generator will also affect that, but I know from experience and reading that the airfoil will be doing that. So let's focus on the airfoil now, and let's say we want to calculate the Reynolds number based on the airfoil. Now, which value do I take? Do I take the chord, the span, or even the thickness? Well, I know from experience and just from theory that the span of the airfoil is not going to really affect the Reynolds number too much in terms of whether the flow will be laminar or turbulent. I mean, if you have this airfoil, which is 10 times this length, it's 20 meters a span, it's not going to really change whether the flow will be laminar or turbulent. When you get to the wingtips, okay, that's a different story. But generally speaking, it won't affect the middle area too much. So I can say, okay, this value is not really that important in terms of determining whether the flow is laminar or turbulent. I know that the chord is actually quite important, because if I were to make this 2 meters, so twice as long in the chord direction, then that means that the flow will go over twice as much distance, and we know that the longer that the flow goes over a surface, the more likely it will transition. And if you don't know that, check out this video here on boundary layers, which we've done in the past. So I know this is probably a pretty important parameter here. Finally, the thickness. Okay, the thickness, I do know it does affect the amount that the velocity, that the flow accelerates in terms of the velocity. So I could always look at that, but generally speaking, I know from experience that the chord is more important in terms of that. So if I were to calculate the Reynolds number, based on the airfoil, I'd usually take the chord here. But that's not necessarily saying that I can't also take the thickness. I could do the Reynolds number for both geometries, both parameters, and just specify them in my report. So I can say the Reynolds number based on the chord is this, the Reynolds number based on thickness is that. So let's say the Reynolds number based on the chord. So now I know that the Reynolds number based on the wing chord, C here, is 1.2 times 1 times 1 divided by 1.79 by 10 to the minus 5, which comes out to be 67,039. So that's for the airfoil. But What about the vortex generator? So even if I were just focusing on the airfoil and the effects of a vortex generator in general, I do know that the vortex generator does affect the flow, because I know that there are vortices coming off here that's going to turbulate the flow, that's going to mix a lot of momentum into near the wall, that's going to affect the turbulence. So perhaps the vortex generator is important in this case, and also maybe, depending on how big the vortex generator is, it will be more or less effective. Perhaps it will affect how much vorticity is created, how much these vortices are rolling up, the strength of them. So knowing the Reynolds number based on them, on this vortex generator, is probably a good idea as well. So even if I'm not interested in the vortex generator too much, knowing about it is just generally a good idea. So I could do the Reynolds number based on the vortex generator's length. So let's say it's 0.1 meters here. So this is 1.2 by 1 by 0.1 divided by 1.79 by 10 to the minus 5, which equals 6,704, just 1/10 of that. And I could also do that for the height, because I know, okay, if it's higher, like poking more out into the boundary layer and even the free stream flow, that means it's going to be sucking in higher moving, like fast moving flow, and that might affect the vorticity. So I could do that as well, and I would come out to be the same thing. I would just have to specify Reynolds number based on the vortex generator, the height, let's say, and then if also equals that. And I could also do it on the width, because maybe the more it fans out, the more it will affect the flow. So I can also put the Reynolds number based on the vortex generator's width and put it here as 1.2 by 1 by 0.2 by 1.79 by 10 to the minus 5, which is double that, which is 13,408. And so now I have the Reynolds numbers based on these different parameters, and I could then process my results, look at each one of these Reynolds numbers, and see how the results were changing based on these Reynolds numbers and how they were changing. And if I find that, okay, let's say the height and length didn't make much of a difference to the flow, I can then discard these and not report them, say, okay, they were superfluous to needs, and then focus on the Reynolds numbers that were important. The important point is noting that if you don't know 100% that a particular Reynolds number in a certain direction is not going to affect the flow, don't discard it. Make sure to analyze it first and then report on it. Because if you do discard it and then not consider it, then that may be just an oversight in the work that you have, and it's not a great idea. It's really easy just to do these and, spend an extra half an hour to get the right answer. So that is how to calculate Reynolds number based on these different parameters and when to use which parameter and how to go about troubleshooting these things. So that is it in this video. If you liked it, make sure to like and click the subscribe button, and I'll see you in this video. Peace and amigos.